Alright, let's get started. So basically, this tutorial is about union find. And for union find, we want to support actually two main functions. The first one is called merge sets. So merge sets takes two elements, I and j, and basically merge the set containing I as well as the set containing j. And then the next main function is same set, whereby we find the set of element containing the element I and find the set containing element j and see whether they are the same set, right? And after that, there are a few helper functions. So this find set, you can find the set size as well. So there's the size of the set containing the integer I, and then finding number of sets. So it shouldn't have a parameter. So finding number of sets basically finds the total number of sets that are currently available. So for instance, if we have an example whereby initially there are 8 sets, so n is equals to 8. So 0, 1, 2, 3, 4, 5, 6, 7, right? So 8 sets, right? Yeah, so 8 sets. So let's say we do a, let's say, merge set, right, of 3, 4, right? So what's going to happen here is that 3 and 4 will be merged into one set, and then if we call it same set on 3 and 4 later, this should return true. On the other hand, if we do something like is same set 2, 4, this should return false, right? Yeah, so the question now is how exactly would we want to implement this union find data structure, right? So a naive implementation might say something like, for each set we'll have something called a parent of the set, and then for all the elements of the set, if you traverse through the parent pointers, you eventually reach the parent of that set. So concretely, how this is going to happen is, for instance, if we merge 3 and 4, right? So what's going to happen is, let's say we have something like this. So 3 has a parent pointer to 4. So let's say this happens after we merge set 3, 4, right? And let's say after that we do something like merge set 5 and 6. So this might be something like this. And then after that we might say something like merge set 4, 5, right? So maybe something like this. And so you realize that the parent of this set is going to be 4, right? Because if everyone traverses through the parent pointer all the way up, they're going to reach 4 eventually. So we can call 4 like the parent of this set, right? So one way to implement this is to basically have a parent pointer for each element, right? So initially all the parent pointers will be pointing to itself, so something like this, right? And so on. So, but eventually, let's say if I want to merge 3 and 4, for instance, maybe in this case, what will happen is that, let's say for instance, 3's pointer, instead of pointing to itself, might point to 4, right? And then we would say that 3 and 4 would be the same set. And so if we were to look into the implementation, let's have the implementation here, right? So we'll have, let's say, a class union find, right? So remember, these are the main functions that we want to implement. So what we are going to have is so some private properties. So int n is just the number of elements, and then we'll have some kind of parent pointer, right? And right, let's go to the public functions. So firstly, let's do is same set, right? Bool is same set int I int j. So what is going to happen here is really what we want to do is return find set I equals to find set of j. Alright, so I haven't really said what find set is, so let's go through find set. So for find set, really what is going to happen is we're just going to find the parent pointer the parent of the set containing I. So how do we do that? So we can do something like return. So we're going to check whether the parent of I is equals to I, and if it is, right, we're going to return I. If it's not, we're going to find set of the parent of I. Right, so something like this, right? Very simple implementation. So if we look back into our example here, right, so in this case we have 3, 4, 5, and 6, right? So if we run something like find set of 6, right, find set of 6, it's going to ask ourselves, so we ask ourselves if the parent of 6 is equals to 6. So since the parent of 6 is 5, so it's not equal, so what we're going to do is find set of the parent of 6, which is find set of 5, right? And then when we are doing find set of 5, we're going to ask ourselves, is parent of 5 equals to 5? So the parent of 5 is 4, so it's not equal. So we're going to do find set of parent of 5, which is find set of 4. So we're going to return parent of 4. Since it's equals to 4, we're going to return 4, right? So if we do something like find set of 6, we're eventually going to get back 4, right? So find set basically finds the parent of the entire set. And so if we go back to a sim set, what it's really doing is trying to find out whether the parent of the set containing I is equal to the parent of the set containing j. Because if the parent of the set of both elements are the same, then obviously the two elements are in the same set. Right? Cool. So the next thing that we want to talk about is this thing called merge sets, right? So void merge sets, right? Int I, int j, right? So the first thing that's going to happen here is we really want to find out whether the two sets are disjoint in the first place, right? Because if they are not disjoint, then you would not even need to merge them. So of course, the first thing that we're going to do is, if not is same set I, j, right? So if they're not in the same set, then we're going to merge them. So the merge code is going to be here. Something like this, right? So the merge code is here. So a naive way of implementing might be just to say that, you know, the parent of one of them, no. So what we have to do first is to find the parent pointer of each set. So int x equals to find set of I. So this is the parent of the set containing I, and int y is going to be find set of j, right? So we can imagine here's I, it points all the way to x, so x is the parent, and there's j, and it points all the way to y, right? And what we can do is we can just say, let's say the parent of x, I'm going to set the parent of x to be y, so it's going to be something like this, right? And so in this way we would have joined the sets containing I and j, right? So because if any element in the future, when I find set, is going to eventually find y. On this side, if I find set, is eventually going to find y, and I'll be able to conclude that they are in the same set, right? So the question now is how efficient is this implementation, right? So what we realize here is that this implementation is actually going to run in on for your the same set operation as well as the merge set operation actually. And the main reason being that you may end up in situations like this, whereby all your elements are pointing one parent pointer to another, right? All the way to the n-1 element, right? So let's say we have already merged all the sets, right? If I'm going to do find set on 0, realize that I have to actually traverse on number of times, right? On number of times in order to find the parent pointer of the set, right? So all the operations actually are done in on. So the question is, how do we improve on this? So the first the improvement that we can think of is really inspired by the balanced binary search tree, right? So in balanced binary search tree, we learned that basically if you want all the operations to work in O log n, right, we have to ensure that the entire tree is balanced, right? So what we're going to do here is figure out how to ensure that this situation does not happen, right? So basically it's going to look more like, you know, something like this, right? So really like a something like this, which is more like a balanced binary search tree, right? So let's go back to our implementation, right? So let's do this again. So previously, again, this is just for comparison, right? Previously, we already have something like int n and int parent of n, right? Yeah, of course, there's a constructor. So since I don't really have space, I'll just do the constructor here. So the constructor is going to take parameter, which we call _n, which is basically the initial number of elements, right? So instead of just a parent array, now what we're going to have is a rank array. So you can think of the rank for now as something like a height of each element. So during our initialization phase, we'll do something like, okay, n equals to _n, right? So that's basically just the same number of elements. And then what we're going to do is something like for int I equals to 0, I smaller than n plus I. You're going to set parent of I is equals to I, right? And that's because remember that this, right? Initially, all the elements have parent pointers pointing to themselves, right? So this is what this is doing. And initially, rank, which we can currently think of as height, is just going to be 0, right? So initially, all the nodes have a height of 0, right? And if we go back to here, right? So the main thing that we need to re-implement is this part, right? We cannot just naively just take one of them and then set the parent pointer to the other one, right? So if we were to expand this, right? So let's do it here. So void merge sets int I int j, right? So once again, we're going to find out if it's not in the same set, right? So if it's not in the same set, we'll first find the set. So find the parent of each of them, right? And instead of just doing parent x equals to y, what I'm going to do now is I'm going to find out if rank of x is smaller than rank of y, right? So if rank of x, which you can think of it as the height of x, is smaller than the height of y, right? What we want is basically the parent of x to be y, right? So for instance, if x is just one element, let's say this has a height of just 0, and this is y, right? So this is y, this is x, and this is some element a, right? In this case, what we really want is for the parent of x to go to y, so it should be this way, right? And else, we want the parent of y to be equals to x. And then there's also the case whereby the ranks are the same, right? I mean, if the height is the same, then it really doesn't really matter which way you point it, right? But if we make y point towards x, then we need to increase the height of x, right? So for instance, if initially it's just like this, x and y, right? And now y points towards x, right? Parent of y is equals to x. Then we need to increase the height of this node by 1. So we add 1 plus rank x, right? So this is really all we have to do in order to make our operations, instead of being O(n), to reduce the runtime complexity down to O log n, mainly because now it's really like a balanced binary search tree. But there's actually one other heuristic. So this heuristic is known as union by rank, right? And the other heuristic is called path compression. So in path compression, if we look back into this example, what it's going to do is during the operation of finding the parent, right? So find set is finding the parent. So during the operation of find set, we are going to ensure that after we do find the parent element, so for instance this, I'm going to make everything point towards this, right? And so on. So in the future, right, if I find set of 0, I don't have to, you know, move through everything again one more time in order to find the parent, right? So because I've already moved through it once, and now I know that the parent of 0 is this, so I'm just going to point it this way, right? And how do we implement this? Very simple. So instead of this, right, we're just going to add something here. So we're just going to say that the parent of I equals to find set of parent of I, right? So basically it's going to just continue doing all the find set operations, but eventually when it comes back down, because we did find the parent of the set to be this, right? So it's just going to set the parent of this element to be the parent of the set, right? And if we use these two heuristics, basically we are able to reduce the time complexity down to something called the Ackermann function, which is roughly linear, right? So unless n is really huge, right, you can think of this as almost linear. So it runs in almost constant, so it runs in O1, right? So what we have done basically is to reduce On to O log n, and then down to O, almost O1, right? Ackermann function, almost O1. And yep, so that